Hello, this is Carl Freund again with Cambrian-AI Research, doing another video with an industry leader. We're going to do something a little different for you today. Instead of talking about really fast silicon, we're going to talk about how one actually gets their software to be able to run on that fast silicon so you can do useful things with the silicon. That's the whole idea, isn't it? To help us understand how this is taking place, I've got Ceze from OctoML. He's the founder and CEO. He's got a very interesting value proposition. He's also a professor at the University of Washington in computer science. So, Luis, welcome to the program.
Thank you very much for having me here, Carl. It's a pleasure. So I've listened to some of your other recordings. Very much looking forward to this. So
awesome. Well, real pleasure to have you here. Let's go ahead and get started. Here's a few questions to get started. Just tell us about what OctoML is as a company. What problems are you helping developers solve?
yeah, so OctoML is building what we call machine learning acceleration platform. The problem that we solve is we help machine learning engineers and data scientists get their models optimized, benchmarked, and ready to be deployed on a wide variety of hardware targets without having to do a whole lot of manual optimization. As we're going to talk through the rest, probably through this conversation, so tuning AI models to make the most out of the silicon that they run on is quite an ordeal, and we've been doing work on using machine learning to optimize that process for a while. It started as a research project and to an open source project that got quite a bit of adoption now to OctoML. So
yeah, so talk about what kind of algorithms and models OctoML can help developers compile to these different platforms, and which hardware architectures can you produce code for today?
Yeah, absolutely. So let me just tell a little bit about the foundation of OctoML, which is this project called TVM, that stands for Tensor Virtual Machine, and now it's Apache TVM. It's open source under the Apache Software Foundation. So what TVM does is it's a compiler, runtime system, and a little bit of an operating system, actually, that takes models from all of the major frameworks like PyTorch, TensorFlow, Keras, MXNet, and so on, and then compiles and optimizes and generates a binary to run on a wide variety of hardware targets. Okay, so and it supports pretty much any model you can think of, right? So we support obviously CNNs, but RNNs, large language models like GPT-2, and transformer models, which are getting very popular, models with dynamic behavior, and so on. It's primarily focused on inference. It has focused on inference, and now we are hard at work at supporting training workloads as well. So then you can optimize the job that's not just when you're deploying the model, but also when you're training and creating the model, optimize that as a workload for your hardware targets, including training. So the hardware that it supports today is the one that's established, that's using production. I should have mentioned. So TVM has been using production for a while. The project is about 5 to 6 years old, and it's used by major AI/ML players like Amazon, Microsoft, Facebook, and so on. But also is being used in production by a lot of ML end users and that have deployment needs, right? So the hardware supports includes mobile and server CPUs with x86, ARM, RISC-V, and MIPS ISAs. We made it very easy to extend. That's one of the key things about TVM is extensibility. So you can extend to new hardware targets or extend to new classes of optimizations and new classes of models very easily, or as easily as it can be. So anyway, so mobile and server CPUs and also mobile GPUs like NVIDIA, Intel, ARM, AMD APUs, or Adreno GPUs from Qualcomm, and so on. Server GPUs, obviously, like NVIDIA and now AMD, working closely with AMD to enable their server GPUs. Also, FPGA backends, as part of the open source project, there is a open deep learning accelerator that's synthesizable in FPGAs called VITA, stands for Versatile Tensor Accelerator. It's more of a template that can be tuned for model characteristics, and then you can use that as the backend for FPGAs in TVM. But also, there's support. TVM also has support for accelerators, right? So ARM has built an NPU. So ARM has actually built a unified CPU, GPU, and NPU software stack based on TVM supporting their NPU. Qualcomm, this is public, they've been building a DSP backend for their Hexagon DSP, which is one of their important bets on supporting high performance AI workloads. And anyways, and there's a bunch of other silicon players that are building their backends with TVM. For example, Sima.ai has been a fantastic contributor to the community, and they've been building a backend based on TVM, and we work with them. And then several others that we know participate in our community. So
interesting. So a lot of my followers are semiconductor designers, and they're building accelerators for edge or data center inference and training. So if I'm one of these companies, how would I get started building the back end? How much effort is that to work with TVM, and would they contact you to start that process, or just kind of walk
they
me
don't
through
have
how
to.
that
I mean,
works?
absolutely, yeah. They don't have to, by the way. So you can participate in the community, and we encourage that as well. We definitely want to see the ecosystem grow. But maybe there's an opportunity for me to back up a second. Like, why make this open source? So
Yeah.
first of all, this is a major endeavor, right? So just think about the fast moving targets of machine learning models at the top, frameworks evolving continuously, and some of the major ones like TensorFlow and PyTorch that are backed by big companies and have significant followers that are evolving fast, and then a wide variety of harder targets. Imagine the cross product of all of this is a really wide set, right? So, and I'm a firm believer that the best way to make this sustainable is to make a thriving open source community around it. Right. So it's truly open. People contribute code from the top to support new models, from the bottom to, and at the bottom to support new harder targets, and then everything in between to enable the optimizations, right? So the way a hardware vendor will get started is first, there's several backends that already exist that serve as good blueprints for different styles of architectures. For example, if you have a typical GPU like multi-threaded architecture, there's a template for that. If you're looking at a decoupled access execute with queues and tensor cores, there's not a template for that based on our work on the open accelerator. I'll get started with one of these existing templates and existing backends. But now what hardware vendors would get here and silicon providers would get here is really independence from having to build everything on top of that and connecting to a framework, right? So first of all, you have to make a conscious choice of which framework you're going to support, which classes of model you're going to support, how you're going to do it. If you're going to do it based on operator libraries, which is what people typically do, they rely, hardware vendors rely on hand-tuned, highly optimized libraries. They have to have a significant need for TLC, right? So tender loving care, that continuously maintaining that to be, up to date with respect to where the models are going, right? So this is a ton of work. And the key thing that CVM will do for them is essentially use our machine learning guided optimizations to produce highly tuned operator implementations for the models that are relevant today without having to build an army of low-level library writers and maintainers that a lot of hardware vendors have to do, right? So I know I probably answered more than you're looking for, but I wanted to give context there that start with a template, build a basic, and then enable the optimized code.
Okay, so you don't start with sand on the beach and try to make silicon. You start with working code and optimize for your particular architecture.
Yeah, which is, it's important too when you're making, obviously you need to make a really conscious decision of what are the aspects of your architecture that are likely to be relevant by the time the chip is out, right? So, these are all these AI silicon vendors are chasing a moving target, right? So if you miss the models that are relevant by the time your chip is out, there's a significant existential threat. So you have two options, right? Either you build more generality, which means that you pay in efficiency, because you're going to pay some efficiency because of that, right? Or you place, very educated bets on what are the relevant models and have a software stack that's just ready to go by the time your chip hits the market, right? So, and to make those decisions, you need early on a pretty good understanding of what's going to make all of these models run well, run fast on your hardware. So that means having a software stack, even ahead of silicon, even when it's really early in architecture definition simulation, you can put these tools in a closed loop design cycle, right? So
it's interesting. I was noticing on your website talking about how OctoML helps companies through that process. There's like a 5-step process, if I remember correctly, and one of them did include benchmarking, so you could anticipate the performance levels you would get through an OctoML, and then actually producing code. Can you kind of walk through
Yeah,
how you
absolutely.
engage with clients? That'd be great.
Yeah, absolutely. So those steps are targeted towards the machine learning end users. And to be clear, OctoML really sits in between machine learning end users and the silicon where these models on. So do work with us. Some of them are our customers, mainly to enable their hardware on TVM and on our platform. But really the end goal and our final broad set of customers are really end users are going to come to our software service platform to optimize and deploy their models. But then answer your question, the 5 steps from the perspective of the machine learning end users and data scientists is they get the model is trained because they're already happy with the accuracy, they're happy with what the model does, they upload the model to our service. And then the model is optimized using TVM. We take what we call best of both worlds. We use TVM, but we also potentially use libraries that are specific to hardware targets. So we get the best of each option such that you're not going to be missing out by using a specific software stack. We want to offer the end user a worry-free experience in terms of performance, right? So they're gonna get the best performance that they can. So anyways, they upload the model, and then the engine does the optimization. That means really breaking down the model into its operators, doing high-level optimization, saying operator fusion or other model transformations, and then generating code that's specific to the hardware targets using machine learning. So let me just take a quick parenthesis to explain how that works, because it's really important here, right? So as I said before, we don't want to rely on hand-tuned optimizations by talented software engineers, right? So the way our engine subsumes that is by really running a large number of tiny little experiments to build a machine learning model that predicts how the hardware target behaves in the presence of certain code optimizations. So then what the optimizer can do is produce a very large space of possibilities. Think of it as billions of possibilities of how to compile your model, parts of your model, to the hardware target. And of course, we don't have time to run them all because billions of experiments, even taking a second, is just too long. So we use this machine learning model to predict which ones are likely to be good. And we only run those. And then with those, we start making decisions refining that model. So, and this tends to be pretty comparable to hand-tuned code performance, which we can talk more in a second. How does the performance compare? So anyways, optimize the model. So once it's optimized, we do that for a set of architectures. So when you upload your model, you can choose all the ones that are supporting the platform. There's a checkbox there. You can choose to click them all. So we're going to run these optimizations and benchmarking across all of them. Some of them are mobile targets. So we have a co-location facility that has, in a rack, all the mobile targets that where the experiments would run, right? And we produce a map to the users on how their model runs in all these hardware targets. They can be used for decisions on how you want to deploy it. If it's cloud deployment, you might want to choose the one that gives you the highest throughput per dollar. If it's on mobile devices, it might be on a set of mobile devices that your model is supposed to run on, and you want to see which ones you were cleared for, right? So it's going to run well enough. And once you make your decision of which ones you want, you would you download the compiled resulting model, which is essentially a highly tuned binary packaged without a clean interface for you to go and deploy with literally a couple of lines of code. Okay?
Wow. That's
and
when
then
you and I
when you go
first
and
talked,
deploy
I
it,
said, this sounds like magic. And you say usually
well,
when something sounds like magic, it's because
there's a lot of
they're using
technology.
AI.
There's a lot of technology behind it, right? So
That's
and for
fascinating.
those that are so inclined, as I mentioned, we have an academic background, right? So this started from research, and there are papers about all of the core techniques here that if they go to our website or search for names, they'll find the papers behind all of this. So
That's great. That's great. You mentioned you'd actually worked on Blue Gene at IBM about the same time I was at Blue Gene. So you know something about the hardware you're compiling.
well, I'm glad you asked. Yeah, so I am a computer architect by training, and at heart, I think about computer architecture as a pretty broad discipline. That hardware software code design is at the core of it. Started my career at IBM Research. I couldn't have been luckier. Worked on the Blue Gene project where we did architecture, compilers, interconnection networks, operating systems, and did my PhD in computer architecture and compilers too. So, and a
Good.
lot of that, was on high performance linear algebra that came back to be super important in the context of multidimensional data structures like tensors, right? So,
Yeah, it's kind of back to the future, isn't it?
yeah, that's right.
With a lot lower precision.
That's right. But a lot more data to make sure that you choose
A lot
exactly the
more
right
data.
precision. Yeah.
Fascinating, fascinating. Do you have any client examples you can share? We don't have a lot of time, but if you have a few names you can throw out,
Yeah.
that would be helpful.
So you see that we have a couple of partners that I want to highlight. You see, like we work with AMD. We enabled their APUs. For example, one of the things we enabled on TVM and show consistently, 2x better performance on their hardware targets. We also pretty close partner with ARM. We supported. They've been doing a lot of the enablement of their hardware. We collaborate with them. And then there are a couple of direct customers of our service that I should name the name now, but I can tell it's a big technology company. It has major AI ML deployments in both edge in the cloud. And in the cloud side, we help them increase their throughput per dollar of large scale computer vision over videos by a factor of 10. So it's a 90% reduction. Could be it's pretty significant when it's a large deployment, right? So, and also edge deployments. So as you know, a lot of apps that we use every day today to interact with other humans. You have models running locally to do image augmentation and background suppression and audio audio filtering and audio denoising. And so we've shown significant performance improvements 2x and plus on edge devices, which it sometimes can be an enabler, right? So yeah.
Well, as the world of AI becomes pervasive, many of us believe that every application in the world will have AI elements, and every computer in the world will have AI capabilities. So removing the software burden of deploying all these millions of applications over the next 20 years is a huge contribution. So.
Absolutely, and I think that if I may make a quick analogy here, I feel like where we are in AI ML software ecosystem space kind of looks like the PC industry in the 80s. You have this siloed, almost monolithic offerings that tightly coupled with the hardware vendors, all the way up potentially to the user and so on. And, disparate, fragmented ecosystem, and having a clean layer across all of these to enable, let's say, more choice for the end user and, more focus on building the model and less focus on work on how they run. It's sort of like equivalent to building in the quote unquote operating system on top of all the other targets that's uniform for model developers, right? I feel like that's our big aim. And there's several others that share this view with us as well. And there's a lot of activity in this space. So it's been awesome to see all the collaboration opportunities.
Excellent, excellent. Well, Luis, thank you for helping explain how you do magic with your software and services. And it's comforting to know that AI is helping build AI, both in silicon and in software optimization. So I think it's a really cool story. Thanks for sharing it with my audience. And let's have you back on anytime you'd like, and maybe we can dive down a couple of interesting case studies.
That sounds great. Well, thank you very much again. And it's been a pleasure. I hope to talk to you again soon.
Hope to talk to you soon. Take care. Stay well.
All right.
Bye.
Thank you. You too. Bye.